Welcome to the second session in the series of 10 sessions.
We're going to discuss the softwares, we're going to discuss the basics, the theory, and some of the equations. Uh, let's begin. A disclaimer, you might want to change your major to aerospace after this session.
I'll just give a quick recap what we discussed yesterday, and then we start with today's session. So we discussed that we defined what push is, and then we discussed that what can we push against to propel our rocket in space. And then we discussed what Mach number is, and we discussed the propagation of pressure waves in any fluid medium. And then we discussed that how does the speed of sound changes with these parameters right here. And then we discussed that how an airfoil interacts with different uh, interacts with air in different flow regimes, that is different Mach number regimes. We discussed about the different shock waves, bow shock and oblique shock. We said that in oblique shock waves, there's less transfer of kinetic energy from aircraft to the molecules, but in the bow shock, there's more transfer of kinetic energy of the aircraft to the molecules. So we said that we have two goals when it comes to the rockets, that we want to throw stuff as fast as possible, and we want to throw as much stuff as possible. So we discuss our goal one, that how can we achieve the fastest way of throwing any stuff. Then we said that we can use chemical energy. We had multiple different options, but the conversion of chemical energy into the kinetic energy was the most efficient one. We discussed the propellant options. Then we discussed what makes something go fast. Like we can only carry our own stuff that we're going to push against. So how can we throw that fast? Then we talked about pressure, that difference of pressure can make stuff move, be it air, liquid, anything. Then we started building that as a rocket engine. Now we said that we need a very high pressurized tank, but if we are going to make it really high pressurized, then the walls of that tank must be very thick, but that's gonna increase the weight by a lot, and it's gonna be unfeasible. So we said that instead, let's add a small, very high pressurized tank to our main fuel tank, and then it's gonna be much better, much more efficient. Then we discussed that if you're gonna so how to make it more faster. Then we discussed that if you're gonna converge our nozzle, then the exit velocity of the gas is gonna increase. But then we discussed that can we just keep on doing that, keep on converging that further and further? We said that no, if you're going to do that, it's going to actually reduce the exit velocity after a certain point. And that is exactly when the flow becomes the choke flow. That is when the exit velocity becomes equal to the Mach 1. Then we said that so instead of converging after that, we're going to diverge to make the pressure drop further and further. Then we discussed that we can have fuel and an oxidizer tank, that is bipropellant liquid engines. So then I want to discuss that we need injectors for mixing two different fuels. So before we can burn two different fuels, like fuel and oxidizer, we have to mix them pretty well. And before even mixing them, we have to make them atomized, because right now they're in the liquid state, and liquids cannot be mixed and burned efficiently. So we atomize them and mix them simultaneously with something called injectors. If you're gonna do all of that, it's gonna look something like this. So here's the injector. The fuel is liquid before the injector. After it's gonna pass through the injector, it's gonna be atomized and it's gonna be sprayed with a high velocity. So now we need some plates that's gonna keep the flow direction constant and uniform. Otherwise, it's gonna be very chaotic here. And then this is our combustion chamber. And then this is the converging part, this is the diverging part, and we call this entire thing as nozzle, and this entire thing as an injector. In real life, it looks something like that. but there could be many different types of injectors. That is, many different ways of atomizing and mixing the fuel with the oxidizer. So here are the different types of injectors. There's one that we just saw, pressure fed injectors. There's something called impinging injectors. If you're gonna Google search about that, they look like that. So this basically sprays liquid oxygen and the propellant really fast into each other, and due to the collision of the molecules, it actually atomizes by itself and mixes at the same time, as you can see here. Then there are something called swirl injectors. Swirl injectors are kind of like the pressure fed injectors, but they have some obstruction right before the end. Like you can see this in this image. So this obstruction makes the stream split radially, and that's why it's called swirl injector. And then there are film cooling injectors. There are multiple different injectors. We cannot go through all of them, but some of them are here. And we need an injector that is optimized for our rocket design, so and our fuel. So we do something called computational fluid dynamics simulations before we actually design in real life and test. So we discussed last time that there are these different types of rocket engine cycles that are possible. Then there's something, then there's a cycle, not really a cycle, but a more simplistic design that you can have a solid rocket boosters as well. If you're gonna make your propellant and oxidizer as a mixture, as a liquid mixture, and it's gonna solidify over time, and then if you gonna put a hole through the entire cross section, through the entire length of your fuel, of your solid fuel, and then if you burned uh, if you started burning it from here, the entire internal surface area is going to burn, and as the time would pass on, it's going to start um, it's going to be burned from inside out in the complete entire length of your rocket at the same time. And in practical life, in real life, it's really efficient, so we do use them in the first stage of our rockets. And we also discussed delta V budget, that how can we figure out that how much fuel do I need to burn and stuff like that. Now in this section, let's start with aerodynamics. So before we can go to space, whatever we discussed needs to pass through the atmosphere. So we need to understand aerodynamics, the forces that air could impart on your rocket pretty well. So in fluid dynamics, there's a drag force formula, which is very simple. It's just some numbers multiplied by the square of the velocity that you're going at times the cross-section area that you're sweeping through that fluid times the density of that fluid. Now, there are different reasons that there are different ways that a fluid can impart forces on anything that moves inside it, be it a rocket or be it anything. Now, those reasons are dynamic pressure, skin friction, interference, drag, and induced drag, then wave drag. But we are going to talk about it's going to take a really long time if we're going to go through all of them. So let's discuss the first two mathematically and build our intuition around it. So dynamic pressure is you can think of it like molecules. If imagine your rocket standing in a grid of molecules. If you're going to try to move your rocket, it's going to hit if you try to move your rocket in this direction, it's going to hit molecules from this side. So imagine that force as dynamic pressure. Molecules hits in the face of a moving object to slow it down, and we call it dynamic pressure drag. And you can think of skin friction as molecules that sticks to the surface. So if you're gonna take a microscope and zoom into any surface, it's not gonna be a perfect if it's not gonna be a perfect plane. It's irregular, and some of the air molecules actually stick to your surface by different forces, um, adhesive forces at a molecular level. So in most cases, the velocity of molecules near your surface, and be it any surface, is zero, is exactly zero. So the molecules cannot move very near to your surface. So, but the molecules away from it are actually moving because your object is moving. So with respect to your object, the molecules are moving, right? So that resistive motion actually creates a friction even in the air, even in the fluid, right? So you can think of skin friction as that. And think of interference drag and induced drag like kinetic energy is being transferred from your moving object to the air molecules due to turbulent mixing of the separated flows. This is kind of complicated. In future, we can discuss this in depth, but let's skip over this for right now. Then we have wave drag. So we discussed about shock waves being formed in the atmosphere in the last session, right? So those shock waves plays a major role in wave drag. They're they can change the entire aerodynamics of your system. Now, how do the forces deforms anything? Let's understand that from scratch, from very basics. So we officially choose to quantify forces by a name called stress. We said that let's instead of calling forces, let's call stress. And we said instead of calling deformations, let's call it strain. And the more stress we apply to any object, the higher is the strain. And the strain, if you're going to plot that for different objects, it's going to look something like this. Let's talk about a typical metal, right? So if you're going to apply more stress, if you, that means if you're going to move along y-axis, your typical metal is going to have more and more strain. It's going to deform more and more. The deformation or strain is on the x-axis. So it's going to look something like this. You're applying more stress, it's deforming more and more. The nature is kind of like this. uh, if you're going to notice something, the nature is linear for for the most part from the starting, unless you're applying a really enormous amount of stress. The nature is actually linear. For if you're going to talk about this region where the nature is actually linear, we can say that stress could be said that some constant times the strain, because they are proportional, right? If stress is increasing, that is left hand side of your equation is increasing, so does the right hand side of your equation. And this is the proportionality constant. We call this constant as modulus. So this defines the relationship between stress and the strain for the linear part. So what do we mean by deformations exactly? So let's actually define deformations mathematically. So it is of different types. So the deformations could be of different types, right? Let's say there's a metal rod and then you stretch that metal rod from both ends. Now the deformation is linear. You increase the length of the metal rod. But let's say there's a metallic block, and on the top surface you applied force in this direction, and on the bottom surface you applied force in this direction. And the block, instead of being like that, it tilted like that. So this is called shear. This deformation is called shear deformation. So right here, I defined linear strain, linear deformation. So let's call that deformation as change in the length. So how much did the length increased when I stretched it, divided by the original length. How much was the original length? So this ratio is called strain, be it any dimension, be it volume. So if I compress something, so how much is the volumetric strain? The change in the volume by my compression divided by the original volume. So the modulus that we just studied right here depends on the strain, right? So so it depends on which strain are you talking about. It's going to decide which modulus are we dealing with. And we quantify stress as force per unit area. So let's say I applied um, a certain force on a cube. So the amount of force that I applied on the face divided by the area of the face of the cube, that is a square, is going to be the strain. Is going to be the stress, sorry. We can see um, the different types of deformations here. This is caused by tension. This is caused by compression. This is the shear deformation that I was talking about. This is bending, and this is torsion. Let's move ahead with the angular deformations as I was talking about. Now, this is exactly my example. On the top face of area A, we are applying a force F on the right direction. It's so the entire cube is being angularly deformed by an angle of phi here. And the top face is moving by a very small distance that we are denoting by delta x. And the height of that box is h. Now, in solid mechanics, the stress is right proportional to the strain. So there's a constant that you can say as modulus that we just discussed right now. Now, imagine a similar analogy in fluids. Let's talk about fluids because our rocket is moving through the fluid, right? So we need to understand how fluid works. Now, imagine that this is a solid surface. Let's say that this is our solid surface of the rocket. Rocket is moving upwards, and we are zooming into the sides of the rocket, how the sides of your rocket is interacting with the air around it. So this is the solid surface, and these are the air particles, air molecules. Now, imagine that this fluid is flowing towards the right. So all of these particles are moving towards the right with different speeds. I don't know. At a distance y from your surface, you're zooming into a thickness like a layer, one of the layers, and you saw that in all of the molecules that fall into that strip that you're studying at a distance y from your surface are moving with the velocity v. All of the molecules in that strip are moving with the velocity v. Now, so if you're going to talk about a different strip, let's say a little bit above this, it's going to be a different velocity. So the v will change with the y. Imagine that we are studying a stack of particles in this situation. We are looking at a stack of particles in this situation. So the particles that are very near, very close to the surface are gonna be are not even moving, right? As we just discussed in the beginning of the session, that the surfaces are non-uniform. If you're gonna zoom in enough, and the air molecules cannot move, they actually stick due to adhesive forces at a molecular level. So and the particle right above it is moving, but with a very low velocity. And as you go up, the particles are moving with higher and higher velocities. Why? Because these particles are really far from our rocket. Now, if you're gonna see a block, if you're gonna study that layer that we just talked about, this layer at a distance y, let's say we are studying a small block of that strip. It's gonna look something like this. The forces on this layer are like this. On the top face, the force is towards the right, and on the bottom face, the force is towards the left. Why? Because as we can see in this graph, let's talk about this particle right here. The particle above it is moving with a velocity higher than this. So it's like that. It's trying to drag this particle in this direction, and the particle below this is moving with a velocity smaller than this. So this particle is kind of resisting from it to moving in the right. So the forces are going to look something like this. Top face will be forced towards right and the bottom face towards left. So it's going to deform like this uh, by a certain angle, and the top face is going to move by a certain distance, right? If you're going to use trigonometry, you'll find out that tan of this angle is dx by h. I mean, how much the top face moved divided by the thickness of that strip that you're studying. Now, assuming that h and dx are very small, you can say that this angle is also going to be very small. And for small angles, a tan of an angle is equal to that angle itself. And therefore, we can write that. And by the way, for the people who are not from math background, you can just like bear me for a couple of minutes. We have some slides, and then we're gonna start actually talking about very interesting things that doesn't involve math. You can understand that intuitively. So people who are not able to understand what I'm saying, you can actually stop me if you have any confusion in any step and ask as many questions as possible, even if I've discussed that and you want me to discuss that again, I'll be happy to do that. Now, this block of, let's call this a packet of water. It's a very small section of the water. So now we can see that this is strained, right? Due to the forces above and below it, this block is strained. And we call this quantity right here as shear strain that we just derived from using trigonometry, very basics. We call this as shear strain. Why? Because this is actually a shear deformation, so we call this shear strain. Take the derivative of this quantity with respect to time, and then you can get this formula v over h, that what's the relative velocity of the top layer divided by the thickness of this layer. You're gonna get this if you're gonna take the time derivative of this quantity. Now, shear strain. Now the shear strain rate inside the fluid mechanics is similar in nature as shear stress in solid mechanics. So just like we studied this, that the amount of force that we apply, that is the stress, is actually proportional to the strain, how much deformation we cause. They're related by a simple proportionality constant, a constant number, right? Um, we can use the same logic in liquids on this shear strain rate. So if you're gonna do that, you'll see that shear stress is equals to some number times this shear strain rate. So higher the shear stress, that is higher the difference in the velocities of top and bottom layers, the more is the deformation, is the rate of deformation of the packet that we were studying, of this packet. I'll repeat that again. Imagine that you multiplied this to the right hand side. You just took this and multiplied to this. Now, higher the shear stress, that is how the shear stress is gonna be more on this packet. If the difference of velocities of top and bottom layers is gonna be more, there's gonna be more shear stress and more of the deformation, more of the angular deformation that we are talking about, right? Uh, and the proportionality constant in this case is called viscosity. So if your fluid is gonna be really viscous, it's gonna be really hard to actually deform your fluid. So, for example, honey is a really viscous liquid, and so it's really hard to deform the small packets of honey. That's why it doesn't flow. The layers stick to each other, and there's very little difference between the velocities of different layers. Now, we derived the formulas for stress and shear strain rate, right? Shear strain rate was V over H, and the stress was force upon area. So if you're gonna substitute those in this formula, you'll see something like this. Now here, you can just solve for the force and you'll get this formula. You can see that this force is directly proportional to the gradient of velocity. And that how much does the velocity change as you go up? That is this graph right here. That how much does your velocity changes as you go up? Your friction force is directly proportional to that. So your rocket is gonna uh, face more drag if there's gonna be higher, more steep this velocity gradient. Anyone have any question or you need some time to digest this? I'm gonna post the derivations I have in on the Discord. So just wait for a while for that. I have all of the derivations here. If anyone have any question or you want me to repeat anything, just feel free to say that. We just discussed that. Now I have an interesting picture here. Now, when we throw a ball really hard, right? So it imagine this ball turning like that. Uh, your ball interacts with air and it could swing like that or like that, depending on how your ball is actually rotating. If your ball is gonna rotate like this, your ball is gonna swing like that, otherwise in the opposite direction. So why does this happen? This happens exactly due to the same reasons that we just talked about. Um, the interaction of air with your ball governs how the forces are gonna act on your ball. So right here, uh, this is actually a bit more complicated than that. It involves the interaction of your ball involves whatever we studied plus what we did not. For example, we didn't study this interference and induced drag right here, right? So if you understand skin friction as well as the induced drag and interference drag, you can actually mathematically derive that how much your ball is gonna move in which direction and how much forces is gonna feel. But you can still understand that intuitively without even going into the math. If your ball is going like this and forward, so the interaction of wind here is gonna be uh, and on the other side, the interactions is not gonna be that much. So the force is higher from this side and it swings like that. Now let's discuss about the first one that we were studying. That is the dynamic pressure drag. Now, imagine a packet of air in the direction of the flow that your object is moving. Now, this packet, let's assume that the thickness of this packet is dx, and the area of your packet is a very small area, so we are representing that by dA. And imagine that the density of your fluid is rho. So the pressure is changing across your flow, right? That's why it is a flow. Um, Now, let's say that the pressure on right hand side of your packet is P, and on the left hand side of your packet is P plus dP. Your flow is from left to right because the pressure on left is higher. So the net force you can calculate like that, and then you can say that okay, this net force is also causing the acceleration. So you can also equate this force with mass times acceleration. So you're gonna get this formula for acceleration. So you can say that your packet is accelerating by this much. Now, if you're gonna solve it further, you're gonna see that uh, the pressure has two terms, exactly two terms, and the sum of those terms is constant. This is another a constant, right? Um, for most cases. But imagine that there are two different objects moving in same fluid. Object A is moving with 10 meter per second, and object B is moving with 20 meters per second. So the second term for object B is going to be much higher. So the static pressure needs to be reduced in order for the sum to be constant. Now let me repeat that again. For the faster moving object, the static pressure term needs to be lower because the sum needs to be constant mathematically. Now this term is changing the pressures, right? So we call this as dynamic pressure term. We represent this by Q. Now I have a personal interpretation of why of how we can understand this mathematical thing intuitively. Now imagine uh, when pushing through the fluid particles, when any object push through the fluid particles in a fluid medium, the kinetic pressure increases. This term increases. Uh, so the so the static pressure, the first term needs to be decreased for the sum to be constant. Now it could be interpreted as if instead of equal number of collisions of molecules from all directions. So right now you and I are sitting in a room and there's gazillions of air molecules striking us from different directions, and but because they're all random and they're all uniform, we are feeling no disbalance of the pressure, that oh, right now I felt pressure from this side more than this side, now I feel more pressure from left. It's not like that, right? So equal number of collisions are happening from all directions, that's why we are feeling no net force. But as soon as if I start to move at like 100 kilometers per second, I'm gonna feel the force from the front. Now the collisions are happening in in a non-uniform way. More particles are colliding with me from the front than from the other directions. You can think of it like that. So the drag force should be directly proportional to the dynamic pressure, because the only thing that depends on velocity in this formula is the second term. No, the this term doesn't depends on the velocity. So the dynamic pressure must be proportional to the second term. So if you're gonna multiply this pressure by area, you're gonna get force, and we call this as drag force. So yes, drag force is actually proportional to this. And if you're going to remove the proportionality symbol, you introduce any constant number, and that's your drag force formula. Okay, so I'm assuming that you did understand some bits of it, and it's going to get clearer as we move on. So imagine a ball and an airfoil design. So I'll ask you a question: which of them is more aerodynamic? Out of this ball and this airfoil design, which of them is more aerodynamic?
The ball.
Mm, no. If you're gonna see this formula that we just studied, if the area is gonna be higher, that is the area that the ball is sweeping, then the drag force is gonna be higher. So here, this has just this much area that is being swept, but the ball has this huge area, if you consider it moving, this huge area that is gonna sweep. So this should be more aerodynamic, right? And if you're gonna make it thinner and thinner and thinner, it should be more and more and more aerodynamic, right? More efficient to be moved. Like you can imagine, like uh, imagine that you are in a swimming pool and then you are moving your hand like that. You're gonna feel it difficult to move. But if you're gonna tilt your hand and then if you'll try to move it like that, it's gonna be easier, right? Because now you are covering only this much area. But in the other case, you were covering this much area, this entire palm versus. So it's the same. Now, uh, now one could think that if you're gonna keep decreasing the area, and then it's gonna be more and more aerodynamic, right? But that's not the case. That's what I wanted to make it clear. So imagine that we are talking about this flow. So this is more and more streamlined. This is yes, your object is going to become more and more streamlined, but the drag force is not going to keep on decreasing after a certain point. So there's a sweet spot in the middle of these. So what is that? That's going to look something like this. Not exactly a ball, not exactly uh, an airfoil. It's going to look something like this. Now the reason being is that generally when we study aerodynamics, we do consider the area, but what we forget is the skin friction. We forget this skin friction. Now I'll tell you why the skin friction is more in this case than in this case. So the ball is undoubtedly the least streamlined object, but there's least skin friction in this. Why? Because the more area that you have parallel to your flow stream, the more is the skin friction, the more is the chances of skin friction. You can think of it intuitively, right? In this case, there's more skin friction. In this case, there's almost no skin friction, only on top and bottom. Now, uh, the pressure drag decreases as your object gets more streamlined, but your friction drag increases as your object gets more streamlined. So there's a sweet spot between the two extremes, and that looks like this. If you're gonna add both of these curves, you're gonna see the total drag curve, which is gonna look something like this. Concept of the area in the drag force. If imagine an airfoil moving in the air, if you're gonna keep increasing the attack angle of that airfoil, the area is gonna be the area that you sweep is gonna be increased, uh, is gonna keep increasing. So exactly, so there's a sweet spot for airplanes to cruise at a particular speed, which has the least amount of drag, but the sufficient lift to keep your airplane at a particular altitude. Due to these two reasons that I also wrote all of these things, so you can just go back to the slides and see by yourself. Now, so what do we learn this for our rockets? What do we learn from all of that aerodynamics for our rockets? Let's sum all of it up. So we saw that there is just one formula for including everything that we studied in the very beginning. This one formula. This formula includes everything that we studied. It is so powerful. The reason being that this coefficient of drag includes the effects of every single thing that we discussed right now. We usually determine this drag coefficient experimentally by simulations rather than hand calculations. So this formula doesn't look like that, right? But this formula still includes the effects of skin friction, and this formula actually looks like the drag force. This coefficient is different from this one. This is CD and this is just C. So they are different coefficients. Don't ever confuse them. So how does this coefficient in this formula changes? Let's study their effect. This coefficient directly proportional to the sum of all of the drag forces, and study how it changes with different uh, Mach numbers. Because a rocket, the the most significant number in our rockets is usually the Mach number when it comes to aerodynamics. Now, for something like this projectile, sharp projectile shape, the coefficient of drag increases as your object keeps getting faster and faster. But after a certain point, it decreases, and then it becomes constant. After after Mach 1.2 or 1.3, it starts to decrease. This is kind of counterintuitive because we saw that the drag increases as the velocity increases. So the reason being is that the effects of all of the forces that we studied, friction, uh, dynamic drag, the interference drag, the sum of all of that uh, have this kind of nature, not any one force alone. Now, you can see the variation for all of these objects, all of these different objects. As you can see that the lowest drag coefficient is of this sharp nose projectile. So, so we're gonna keep this kind of nose cone for our rockets. That's what we take away from all of that. And um, the variations along the altitude is also very significant. So pressure, density, temperature, and the speed of sound changes as you go up or down in the Earth's atmosphere. This is the variation of all of that. Now, there comes a point when we are taking a rocket through the atmosphere up to the space, there comes a point where if you increase the speed of your rocket beyond a certain Mach number, or if you're gonna keep pushing your rocket is literally gonna break. That point is the point of the highest pressure. That is the maxQ. Now, as we study that the altitude changes all of these parameters that our drag force is dependent on. Now, if you're gonna consider these variations along the altitude, and you will plot the altitude on the x-axis and the total amount of pressure that your rocket faces on the y-axis, you're gonna see this red curve like this, and the highest pressure is somewhere in the lower altitudes where the air is quite dense and the speed of your rocket is actually increasing pretty high. So we throttle down our rocket engines at this point because we don't want our rocket to face that much drag. Otherwise, it could literally break. So we throttle it down from, let's say, 100% engine thrust to, let's say, 70% of the engine thrust. And it looks something like this. So now, instead of getting this much pressure on our rocket, we just have this much pressure on our rockets. And yes, it does actually slows down our rockets, and it takes more time for our rockets to go up in that case, but we prevent our rockets from facing such insane amount of pressures. Now, let's discuss how we prevent our rocket from melting itself. So the combustion reaction produces such like heat in such amounts that could actually eat your metal away and turn the solid into gases. So we don't want our rocket engines, the nozzles of a rocket engine where the combustion is actually the most aggressive. We don't want it to melt away or being eroded slowly. So we need to cool that. We need to cool our rocket nozzle constantly as our rocket goes up. Now, there are many different ways that we could cool it down. We could actually use a heat sink or like for example in our computers in the CPUs, if you're gonna see radiators, that is the metal blocks, they are nothing but heat sinks for taking the heat generated by your CPUs or any processing units away and spread it across a huge surface area so that it could radiate and conduct the heat faster. We either use this, we add um, patterns or textures to the actual nozzle, the outer surface of the nozzle, and we we use thick walls. So let's say that we chose such an alloy that actually erodes or actually that actually erodes. Now the heat of your now the heat that was originally be supposed to transfer to the rocket nozzle and then melt your rocket nozzle is now be actually converted into the is now actually being used by the metal to convert itself from solid to gas. So all of the heat just converts your metallic, your solid metallic rocket nozzle into gases, and the heat is not being able to melt the rocket nozzle itself. Yes, your thick walls actually becomes thin over time if you do that, and it's just one-time solution. You cannot reuse such solutions. Now, what should be now? What other solutions can you think of? What if we decreased the amount of heat energy generated in our reactions, in our in the combustion reaction? So we can actually do that by changing the ratio of your fuel and propellant. If I mean fuel and oxidizer. Let's say the best ratio for getting the maximum heat is you need two unit volume of your you need 2 unit masses of your fuel mixed with 1 unit mass of your oxidizer, and then you mix them and then you burn. Let's say that produces the maximum amount of heat. Now, if instead of 2:1, you're gonna use a ratio, let's say 1.8:1, the temperature uh, of the gases produced in that reaction is gonna be lesser than the idealistic state. So you basically deviate the ratio of your fuel and oxidizer from ideal to a little bit away so that you don't reach that high of the temperatures that can actually melt and sublimate your solid rocket nozzles. Now, we do that by controlling the valves. So our fuel tank and everything is pressurized, right? So we can actually use valves, different valves to, we can say that instead of opening the valve fully, I'm gonna open that valve to 90%. That's gonna decrease the amount of fuel that you get. We can do stuff like that. Or we have one more option. We can do regenerative cooling. So regenerative cooling is looks something like this. In a previous lecture, in the gas generator cycle, we discussed that. I mean, in gas generator cycle, just a second. Or let's just discuss this. We studied this bipropellant liquid rocket engine. What if instead of burning this fuel directly, we actually take this fuel? This fuel is right now cold. This fuel needs to be heated up and then being burned. But instead of directly burning this in the combustion chamber, what if we redirected this fuel into a rocket nozzle in the walls of the rocket nozzle, and then we took that fuel back and then burned that. So the fuel is being heated by the energy that was originally actually melting your rocket nozzle. Now you put that wasted heat to some actual good use. So this is exactly what regenerative cooling is. Here you can see these pipes, right? So the pumps pushes the fuel into these pipes, and then there are small, very thin pipes moving all the way, uh, moving in the entire surface area of the rocket nozzle, and that takes away the heat generated by the gases inside the combustion chamber and the rocket nozzle into the fuel before burning it. I have a really good animation here to show this. So the fuel here actually flows down from these pipes and then is redirected back. Now, as this fuel goes from here all the way up and then comes into the combustion chamber, the heat from these gases actually is being used to some good use instead of melting the nozzle itself. This is one of the best ways that engineers design This is the reason that why rockets exist. So now there's some more ways. Like there's a very interesting way. Uh, it's called it's called film cooling. If you're gonna see right here in this animation, you can see that this is the injector that we just talked about, right? This is every single hole is actually spraying the liquid oxygen and your fuel and mixing them and then burning them. What if on the holes on the outer edge you take pure fuel? Instead of mixing it with oxygen, you take pure fuel. So as you can see right here, this red layer all the way, this is pure fuel. You didn't mix oxygen inside this stream, this part of the stream. Now it cannot burn without oxygen, right? So it's gonna act like an insulation layer to prevent the heat from flowing from here to your rocket nozzle. So this is one of the most genius ways that you can prevent your rocket melt itself. Also, if you're gonna use that method, then due to incomplete combustion, you're gonna produce soot. Soot is like, do you guys know what soot is? Soot looks like this. So if the combustion is not complete, then this solidified carbon actually deposits on the insides of your wherever your combustion is happening, your exhaust and the combustion. And it could be a lot when it comes to rockets, because in rockets, in 1 second, you actually burns thousands of kgs of fuel. That number is like crazy to even imagine. Like in just 1 second, how much fuel does SLS burn? Second. 5.5 tons of propellant per second, like 5,500 kgs of propellant every second. That's insane. So imagine the amount of carbon soot that's gonna be produced if you're gonna use it in your rocket. So this could actually clog the injectors of your rocket if you did it in a wrong way. So you need to be very precise and very accurate in how you implement this. This idea is really good in itself, but it could turn into a disaster. Now, there's one more point. So this soot layer that we just saw actually adds one more insulation layer in the walls of your rocket nozzle. So this makes this method even better and even more effective. But if your pressure if the pressure at any point inside your rocket nozzle increased beyond 1200 psi, then the soot layer that is formed on the insides of your rocket nozzle is going to be eaten away by the flow, and then your flow could easily transfer the heat to the rocket nozzle and melt it. So you need to be it's really hard to implement. That's my point. Now, anyone have any questions? I would like to say something. I wanted to start Open Rocket software today, but now we don't have time. So it is actually we discussed the software in the first session of before winter breaks. So some of the people do know that, but some don't. So anyways, I'm gonna cover this, but now we don't have time, so I'm gonna push this in the next session. And this is like one of the most easiest softwares in our entire stack. So we can cover this entire software in like 20 minutes. I'm gonna sum both of the sessions, yesterday's and today's, in this slide. So this is SLS, Space Launch System, developed by NASA. It is a successor of Apollo 11 that took the humans to the moon. And this has 4 liquid rocket engines. It's called RS-25 engine. And they have 2 solid boosters These solid boosters actually are being used in the first stage. They helps the rocket and the entire thing to move up to the rocket. Move up to a certain altitude, and then they are detached and thrown back to the ground. And from there on, the other engines carry this on. And this is the uppermost stage. This also have an engine. It's RL10 engine. Everything inside a rocket is controlled by electronics. That is all of that is a part of avionics, which is one of the subsystems of our rocket. So we right now we didn't even start avionics. In avionics, we are gonna write flight softwares. We're gonna write some of our own simulations from scratch, and we are gonna write softwares to analyze the telemetry data from our rocket live. So any CS people or anyone interested in softwares is gonna really enjoy. We're also gonna make our own computers from scratch from this software called Eagle. Let me open the software itself. We're gonna program our own computer from scratch. Oh, it logged me out. Okay, never mind. And finally, after winter break, we're gonna start building those rockets. So I hope you guys are as excited as I am.
32 seconds into the flight. 3 liquid fuel main engines, throttles transonic, 2% of rated performance down in the bucket, reducing the speed.